moves really fast. So really excited to learn more about the recent developments, but also different trade-offs. And so today we have 4 panelists who are experts in their PT domains. How about we start with some round of intros and then maybe a short introduction of your project, and then we can start with you, Kurt.
Sure. Hi, everyone. So I'm very happy to say this is my first Web3 event I'm ever attending. Happy to be here and meet everyone. I'm Kurt Rohloff. I'm CTO co-founder of Duality Technologies. We're commercializing privacy tech such as homomorphic encryption, and I'm also one of the co-founders of the Open FHE project. And I'm always happy to help build community and get new users for our open source library. Thank you.
Hi, everybody. My name is Nerla. I'm a PhD student at UIUC, and my research is all about using trusted execution environments in this decentralized context, and what problems come up when you use this technology across multiple untrusted parties like we have in the decentralized world. And yeah, so the last year I've been part-time at INCO, advising them on how to actually use Ts effectively.
Hi again, Lukas. Now I'm maybe turning it to TACEO. So the company behind us is building a private shared state network. So leveraging MPC and co-snarks to make private state composable.
Yeah, no mic for me, I guess. Yeah, I'm Pedro. I'm a DevRel engineer at Aztec Labs. We actually have 2 products, I'd say. One of them is Layer 2, which is, I guess, the most known of, which is a privacy-focused Layer 2 on Ethereum. And the other one is a zero-knowledge language, domain-specific language called Noir. So yeah, it's all about ZK.
Yeah, so the first question is, let's zoom out a little bit. Why work on privacy? What's exciting about privacy to you guys? And what's your thesis on this category in crypto?
Yeah, I can start. It's just it seems like it's the only possible way to do things. We do have a ton of things that are public and private in our own lives, everything we do. And that's just a human right. So if we have some kind of technology that doesn't have both the public side and the private side, and it's very difficult to actually bring what everyone is looking for, bring in the billions or millions of users. And more than that, it's just I guess avoiding that, just avoiding everything being public. It's just it's kind of scary to think of a future without privacy.
So one of our main theses at Duality Technologies is that there is tremendous value from collaboration on very sensitive data. Typically, data in itself is both very dangerous, but also kind of useless at some level. I mean, at some level, who cares what my individual medical records were 5, 10 years ago at some level? I do, and there's probably very few people that can actually exploit that. But at the same time, there's for good reason, very good regulations around the ability to kind of share and collaborate on this kind of data. It would be tremendously impactful for society for medical researchers to be able to access and accumulate data from multiple geographies, multiple places, and get value from this data in terms of new cancer treatments and things like that. We see the need for privacy to both enable these kinds of data collaborations while still satisfying regulations and other kinds of requirements to provide basically better improvements of medical treatments, good governments, protection from things like financial fraud and other kinds of crimes like that also. Thank you.
I guess the reason I want to work on privacy is just, I guess, my own personal paranoia. I just don't want my information out there. I don't want people to know everything about me. And I guess my thesis on this space is I'm really excited about the use of all of these privacy technologies together and how they can leverage one another. Because I know my research on Ts, I end up having to use MPC for stuff. So I think it's really cool to think about how we can take the weaknesses of some technology and like combine them with the strengths of others.
Yeah, basically, I think a lot of things were already said. I want to use a quote from a colleague, like decentralization without privacy is like surveillance without a middleman, and I think this pretty nails it. So I'm a pretty big fan of decentralization, but if we cannot get privacy into the decentralized tech, then I would wish that we had never have had the Bitcoin and whatever to start this all.
So everyone here is a really strong expert in a specific PET. How about let's talk about each PET one by one, how it works, and any exciting developments that happened in the past year or years that are worth mentioning.
Sure. So basically, the core concept of homomorphic encryption is that one can take data, encrypt on the data, and then compute on that data while it's encrypted without having to do things like shared decryption keys and things like that. I'm an electrical engineer by training, and people ask me, like, how does this work? I think about typically the embedding of signal inside noise, special kind of noise that one can basically remove via decryption using something called the decryption key. Well, you guys know what decryption keys are. I don't need to tell you. And so, this is kind of the basic premise of homomorphic encryption. There have been a number of innovations in the space overall. I've been working in the area for the past few years, and the general trend that we've been seeing is roughly an order of magnitude every year or so performance improvement overall. The two highlights, and I'll give you two for the price of one, Remi, if that's okay, is, one is the first commercial hardware accelerators for homomorphic encryption are hitting the market. I'm aware of several companies whose products have come back from Foundry and are about ready to kind of hit the market. And the other is that there's been a number of nice advances about how one can use this advance called what we call programmable bootstrapping, which is basically this core operation inside homomorphic encryption that's kind of like the heavy, hard, big rock bottleneck for computation about how to basically increase throughput through this operation by an order of magnitude. And so that's the order of magnitude, basically an order of magnitude performance improvement, both from hardware and design. You get two for the price of one this year in terms of performance improvement. Thank you.
I guess I'll go next. So the way I usually think about a TE is just it's some kind of like black box encrypted memory region in your CPU that there's like a key embedded in the CPU that only the CPU can decrypt the memory of the TE. So, one of the major things about TEs is that you have to trust that the hardware manufacturer has done this implementation and they're not like trying to screw you over particularly. So I think one of the cool like emerging advancements, not fully ready yet, but a lot of people are thinking about how do we design these TEs to be open source and like so we can kind of take away the middleman of the hardware manufacturer from our trust in the TE hardware itself.
Cool. Yeah, for MPC, it's really hard to describe what MPC is because MPC is more of a subfield of cryptography and a problem than a technology. So MPC consists of dozens and dozens of different protocols. Maybe the most intuitive one is called Shamir secret sharing or linear secret sharing. So where you split your private data into chunks and you kind of encrypt or randomize them, send to each party that participates. And so each party does the same process with its input data. And then kind of the linear functions, so additions, everybody performs on local, and also the multiplications. But here comes now maybe a bit of similarity to, on a high level, to FHE. You introduce an error by doing these multiplications, and you kind of have to get rid of it. Like whereas you're doing FHE, you're doing bootstrapping to get rid of this, or one way to get rid of it is bootstrapping. In MPC, you do an interactive protocol to kind of cancel out the error, and doing this for each multiplication, or at least each multiplication round. The most exciting thing in MPC land specifically for blockchains, I think was CoSNARKs, like the paper 2021, because like this combining ZK with MPC now allows to have verifiability, even maybe you was not among the MPC committee, among the parties that actually did the job, you can trust the integrity of the computation.
Yeah, zero knowledge is, I guess, kind of a, people refer to that mostly as for the succinct property, where you would be able to aggregate multiple operations into a very small and verifiable proof. But that's not what ZK is about. ZK is about the privacy. It's about doing that in a way that also doesn't reveal any or part of the statements you're actually trying to prove. So it's a bit of a kind of a black magic where you make a computation over certain inputs and then share the result. The result can be verified. It's short. It's easy to verify in a non-interactive way, but you still don't have to reveal all the inputs. So that's what ZK is about. Yeah. Again, people usually focus just on the fact that it's a small proof because it's actually very useful for blockchains where you can have very big state changes and operations and make them verifiable in a smart contract. And that's definitely useful, but that's not what we are about at Aztec.
So there are a lot of acronyms here. How should the audience really think about what use case or what PT to use for what use case? So let's go around again and maybe name one use case that you think best represents the advantages of your PET, and then alongside maybe what are some trade-offs that you think are worth mentioning. So maybe we can do the reverse in order. Yeah.
Yeah, I guess the biggest, the use case for ZK, I guess even in Web 2 it's very, very useful because you could do like bank transactions where you can prove that the actual transaction was made without revealing the details of the transaction, like the amount, for example, and just keep that private. Another example would be, for example, for voting. So you could basically vote and being able to verify that your vote was being counted for the final tally, but without revealing your vote, which is kind of essential for the democracy that you don't reveal who you voted for. And so that's an example. I guess the trade-offs is that it doesn't solve everything that we wanted it to solve. There's definitely just like Lukas will probably tell you just now, there's a ton of problems that involve like shared state, shared private state, for example, that it's just not possible to do with ZK. Like if you want to prove the intersection of two sets, for example, you just can't do that easily with ZK. You need other techniques like TEs will do that very well, FHE definitely, and especially MPC, which is we are very excited about that.
Yeah, I think the key differentiation factor from MPC and those four is definitely collaboration. So it's the only one that goes beyond two parties. So every time you have some use case that consists of more than two parties, and usually we want to have blockchains with more than two users, MPC is kind of in the mix of the solution. So I think this is like where it's a big differentiator. And
so just to follow up on that and clarify, one you use, so would MPC be best if you want to use among your friends, or is it okay to trust another group of people running the MPC network to compute on your behalf?
This depends on the use case and the trust model. Like if you want to have peer-to-peer networks, or if you are okay with outsourcing something. Like on the blockchain, you also trust that like 50% of the nodes behave honestly. People are usually okay with it if the economic security is high enough. So if you're going from the trustless model that you can get, peer-to-peer is always the best. And even, like as you mentioned, I think before, ZK alone is best. Keeping your data yourself, not collaborating with anybody, can't harm you. But you don't. It's not fun then.
On the use case, I'm kind of curious. So you mentioned that there are use cases that are difficult to solve purely using Aztec or NOR, but maybe with TACEO, it could be solved. So is there a specific use case that you could help illustrate, how this, utilizing TACEO, we're able to basically solve something that wasn't feasible, still sticking to ZK?
Yeah, it's a bit out of my league, actually, but I guess just the ability of keeping our privacy, but still allow someone else to prove for you, for example. I think this is something that MPC could help you. Just you make the witness generation, for example, and then the proving is done by another party. And this is useful because sometimes you just don't have the resources, for example, to make a big proof. So we could just do the witness generation and have that, which is already private enough, and then you just have someone else that can prove that for you for a fee or whatever. So that's I guess an easy use case. Lukas will tell me if I'm wrong, but I think that's doable. Yeah.
I think what we really know how to use T's well for are these applications that are like require fast performance / like your data is only going to be private for a short amount of time. So the main example that I can think of is like block building without like MEV extraction. So I know Flashbots has like been successfully using T's to do their block building, and they have some kind of guarantee that they're not like extracting MEV from you. So if you want to use T's to like have some private data for long term, I think there's like a lot more stuff that people haven't like considered about T's. I'll plug my talk because I feel like I go into depth a lot about like the other things you have to think about when you're using T's for long-term privacy. So yeah.
So just maybe dive deeper, a little bit deeper on that. Why is it problematic to have long-term states using T's?
Basically, like the T guarantees that you get is on a certain version of your code. So, I mean, if you want something long-term, you're definitely gonna have to update your code. So how do you get the T to actually update the code and still have those privacy guarantees without like introducing some kind of backdoor into your TE? So that's like one of the major problems. The other one is like, what if a TE vulnerability comes out? Like, what do you do? How do you respond to that? So those are like two hard questions.
Sure, no, great responses overall. So I think about fully homomorphic encryption, or FHE, as kind of the Swiss Army knife of the various kinds of privacy technologies. I fundamentally believe that no one privacy solution is a panacea. Nothing solves everything. They all have their bits and places, and like a good cook uses every tool in the kitchen, and you should use every kind of privacy tool on the case-by-case basis. Where FHE is particularly useful is that it is post-quantum, meaning resistant to these emergent quantum computing attacks. So particularly if you really need nation-state adversary protection, FHE is a good solution if you have it properly parameterized, of course, with that caveat. Another nice thing about FHE is that it is quite malleable in how various data providers, computation hosts, and data consumers can interact. MPC is a great solution. It does require online presence of the various kinds of participants in the computation. What you can do with FHE is that you can basically move data from a data source to a computation host, and multiple computation hosts can still collaborate in an MPC-like manner with various what they call threshold variants of fully homomorphic encryption. And so, of course, it has these niches too. Of course, it can't match the performance of TE, and I totally buy everything that you're saying. We at Duality have gone full spectrum, and we're starting to move across multiple privacy technologies. And although I've been working FHE and it's for 20 years or 15 years, and it's near and dear to my heart, I am a big fan of TEs also, and I'm glad it's getting its due also now.
So Kurt, you come from a very strong cryptography Web 2 background. You have contracts with governments, you work with large institutions. Do you see a difference in terms of requirements for FHE in Web 2 versus Web 3 in general?
So I'm saying this as a Web3 outsider, so please be forgiving for me, and please correct me also. I would love to be better informed, kind of as it is. My perception with starting to dip my toe into Web3 space is it's very fast and loose in a good way. You know, build stuff and you know, see what works kind of domain. And so there is broad acceptance of less well standardized, less well proven, less well validated solutions overall. I work in a space, I come from, I started my career as a defense contractor, you know, no hiding it. You looked at my LinkedIn. And particularly if you're working with governments overall, is they have a large acceptance of technical risk to a point, certain kinds of technical risk. And the more that they can validate and look at the underlying privacy technology and understand it, the more accepting they are. And so we fundamentally went early days fully open source with our FHE technologies, specifically to drive adoption for the large enterprise houses, kind of as they are, and have very early on championed both industry consortia and broader government engagement in standards and regulatory acceptance of the technology too, which has been a little bit of friction, but once you get over that hump, it makes things a lot easier once you're kind of flying past those places also. So it's a little long-winded, but there's a lot of nuance there too.
So one thing at least I notice, you know, for something like FHE in Web 2, it seems like people don't care as much about verifiability. It seems like, you know, there's less this requirement you need to generate some kind of ZK proof or even have a need for MPC, right? I guess on the topic of verifiability, maybe I think it's an interesting topic. How does your PET look like in a verifiable version? So maybe it already exists today, right? Or maybe it doesn't, but what will be the next iteration for something more verifiable for Web3 purpose?
Yes, I mean, it's kind of a hot take in the sense that you don't necessarily have to verify all the time, which is fine for some use cases, and for some it's not fine. And so that's pretty much where ZK stands, in the sense that maybe you just don't need ZK, as just maybe you just don't need blockchain, or maybe you just don't need TE.
Also, why are you saying this? I'm kind of curious. Why do you say maybe we don't need to verify?
Yeah, I mean, there are many situations where just the fact that you are doing something client side, for example, you don't actually need to verify that as long as you control your own machine. So not everything needs to be distributed, and not everything needs to be verifiable by everyone. And so yeah, that's pretty much what I mean. Yeah. So just client side, like if you're doing AI, for example, if you're doing AI, you have run your own model in your own house, in your own GPU, whatever. You don't need to verify that, so no need for ZKML stuff. You just run it locally.
Yeah, I think the future, as I outlined for verifiable MPC, is co-snarks, so combining it with snarks.
So who demands verifiable MPC today? From what you've seen, like who would be the right audience for your technology?
Blockchains, like I'm completely sure that like Web 2 doesn't care a lot about verifiability. I think like we haven't seen ZK take off in Web 2 at all. I think it will be more about privacy, not about verifiability. If it goes to Web 2, like this is what we have seen with like the European, for example, identity and so on. Their ZK is interesting for them, but from a privacy perspective, not from a verifiability. Well, it's both, but like not verifiability without privacy.
I think for TEs, like the thing that's kind of underappreciated is like you do get the privacy, but you do also get the integrity guarantees. So if you think about just like taking a Web 2 application and putting it at TE, now you kind of like get a guarantee of like what that actual Web 2 application was doing. So if it's promising to like ask a question to ChatGPT for you and then get back an answer, you might not care about like the privacy of the question you're asking, but you might care that they're actually asking ChatGPT and not just some like random AI model. So I think, yeah, so TEs definitely give you verifiability, and that is really useful for like, I think any application, honestly.
maybe I can ask a question. I'm curious if you think that TEs are better for privacy or for integrity, or it doesn't really matter?
I think it's like, I mean, it's the same kind of level of guarantee, I guess, if you want to make the argument that TEs aren't completely trustworthy. I mean, the integrity and privacy there is all based on the same like level of security, I would guess. So I wouldn't say it's like better for privacy or better for verifiability. It's kind of like the same thing, honestly, for TEs at least.
Okay, but maybe like privacy, you have some short-term stuff, and integrity. Are you aware of any integrity applications that only need short-term integrity?
Short-term integrity. I'm not sure what you mean by
I think you
short-term.
first mentioned like you should use TEs for privacy stuff that is like not too important in 10 days anymore or whatever. If there's some similar concept where you get some integrity from the TE, but you cannot rely long on it.
I can't think of anything, because to me integrity is just like a one-time thing. Like I proved I did something at this point in time. It's not like I don't know, like in 10 days I don't care if I actually did it. It's just like at this point in time I did this thing. So yeah.
Makes sense.
Yeah, I will actually put forward, to get on the TE hype train kind of for what it is. A big thing that we've seen in the space for TEs is the kind of native capabilities for attestation overall. Particularly with the Intel TDX technologies that have been out for about a year or so, it provides kind of a really nice framework for decentralized attestation, and Intel's been pretty good about putting out reference implementations of these capabilities. I don't know if you guys are looking at this kind of thing at INCO, but for us it's been a bit of a thing, and it's been nice overall.
Yeah, TDX is really cool.
I think a good example of these technologies working together actually is what, for example, World is doing, because you can actually you may want to use these for the for the ML part of the process where you want to derive whatever hash they do with the arrays and stuff like that. But then you, as a user, you actually keep that in your phone, and then you want to use ZK to prove things about that. So you want to prove that you are a unique human, for example. And so this is an example of some of these technologies not doing the job by themselves, but working together. They definitely they complement themselves. And I know we're all talking about 4 technologies, but there are other privacy techniques that are out there. I guess these ones are the ones most relevant for Web3, and that's why we're probably here. But yeah, it's also useful to not forget that there's way more than just these 4.
So let's maybe go into like the bottlenecks of each of these PETs and how you think they will be solved, and also when, roughly what timeline?
FHE has bottlenecks. I'll put it a little bit differently. Maybe where FHE is, we are sidestepping bottlenecks. Inherently, FHE, as much as I put it forward, rightfully so in my mind, as a Swiss Army knife for privacy technologies, it very deep computations, things like training machine learning models and things like that on encrypted data, is impractical for general use. I would rather use a TEE, unless you have very special kind of security considerations and things like that. Where we typically sidestep these kinds of challenges and are commercializing homomorphic encryption is issues where the bottleneck is not in a automation technology, but where you want to start to automate a human-driven process. And so we work a lot in gov space and enterprise space, like medical domain and financial services, where there's various kinds of security processes like KYC, know your customer, financial crime investigations, or aggregation of medical data for cancer research centers, where the main bottleneck is basically lawyers signing MOUs, NDAs, all kinds of things like that, which might take days, weeks, months, super expensive overall. And by using privacy technologies such as FHE, you can sidestep a lot of these administrative overhead, make science more efficient, make government more efficient, and basically move things that take days, weeks, months, and have them run in seconds or minutes overall. And that's kind of where we see the sidestep, at least at the bottleneck.
I guess I wouldn't say there's like a bottleneck for use of TEs because it's already there. You can already use it. I think it's more of a problem of like getting the best security guarantees out of TEs that we can. What I found like in my research career is that people kind of see TEs as like this catch-all thing. You could just throw anything in there and automatically it's like private and secure. But like what I like to focus on is like the kind of that boundary between like getting something into the TE and taking it out and like how that process can go wrong. So I'm super interested in like trying to like make sure that that process is super secure. And the other thing is like, you know, the hardware manufacturer that's in between you and the TE. So one of my colleagues here, Sylvain, is super into this topic about like open source TEs. And he's like super deep into that, so you can ask him all the questions about that. But basically the idea is like we want to have a TE that, you know, is open source and like we can actually verify the hardware and we like know that it's an actual real TE, it's not backdoored. So I think those are the, I guess, bottlenecks with TE adoption.
Sylvain, what's the timeline for something like OpenTE?
Yeah, I think Sylvain is like the one that's pushing everybody to do it. So we're all dependent on him to push us forward.
Yeah, I think like for MPC and then a more general bottleneck, so I will explain two bottlenecks. I think MPC lacks a lot of funding. So I think the theoretical background and academic literature is very rich, but actually people drilling down the constants and implementations hasn't been really done. And I think we saw with CK what is possible if a lot of money gets thrown at this problem and a lot of smart people are working on it. So I think this is really a bottleneck for the industry. And the second one is more like generally for private shared state. I think this is really a new frontier, and app developers, even if like it would be performant and it would be a nice DevX, builders would have trouble to think about applications that they can build that are completely different from Web 2 applications. So how do I build an app that doesn't monetize data? Like, you're trained for 10 to 15 years to think in this direction, and now you say like, no, exactly do not this, start from scratch again.
For ZK, I think the two bottlenecks. One is the proving, I guess, the proving cost, proving size, proving. There's multiple ways you can go about it. Maybe you could get faster proofs, but bigger proofs, or smaller proofs, and then not so fast. And so I guess this kind of proving time is a big deal. You wanna these computations to be done on phones and handheld devices, because again you want them to be kept within your device. So that's maybe one of the biggest bottlenecks. And I guess the second one is probably just it's kind of a recent technology, and we're all like playing with these kind of things, but we are using hashes that are not battle tested. We are using this kind of cryptography that's kind of edge. And so I guess it's just a matter of time before things become more standard. This kind of cryptography becomes more widespread, maybe more battle tested. So yeah, there's definitely some cold water to put on top of all the heat from ZK being the best thing. I guess we need to be aware of the fact that this is a very, very recent technology.
Yeah, so it sounds like the bottleneck question is different for everyone, right? It could be speed, security, and yeah, different angles to optimize over time. So the last question is really, what is your favorite privacy use case that you'd like to see happen this year?
voting. I mentioned voting because it's I guess it's one of these problems that was never solved. Really, we all want electronic voting and everything, and we forget that with electronic voting, it's as easy to forge multiple votes than it is to forge just one. And that's something that is not the case for manual voting, where to forge many votes, it's linearly more complicated than just forging one. And so that's an example of a problem that everyone wants to solve, but it actually comes at a huge trade-off in terms of democratic problems. And so, yeah, I want to see this I want to see this. I want to see elections, even small elections, pilot programs, and things like that to be done, to be experimented by governments, by entities, organizations. This year, I think that's totally doable. It's just a matter of like someone picking that up and actually going through with that.
So if we're thinking about 2025, on the infrastructure level, I'm really excited that like Alio launched last year and Aztec is hopefully launching this year. So seeing this first private chains live is pretty exciting and hopefully seeing some traction there. On the app level, I'm pretty sure we see a lot of more application around decentralized identity and looking forward to this.
I think one that I'm really watching closely is this private AI stuff, because AI is really like going crazy right now and it's improving rapidly, and I think privacy and integrity guarantees can really not curtail the growth, but just like make sure it's growing in the right direction, I guess.
Is this beginning of Skynet to private AI and TE?
I hope not. I hope maybe they can use T's to not make it not Skynet somehow.
For me, in kind of the world where I play, more in the Web 2 space, it really is about driving acceptance of the privacy technologies. Two things that I'm watching in particular is, one is NIST has been putting quite a bit of effort into the general acceptance of privacy technologies, and threshold FHE in particular. And I'm looking forward to a call from NIST around an emerging threshold FHE standard effort, which I'm super excited about. The other one I'm very excited about is generally international and transnational acceptance of privacy technologies writ large to move regulated data across international boundaries. The ICO, Information and Commissioner's Office in the UK, has been leading the way on this. And they sit in this really nice, interesting spot where they're of the kind of the genre of English-speaking countries, but also formerly European, maybe future European also, where they kind of play both sides of the street. And with them leading the way, I'm looking forward to more general acceptance of privacy technologies, particularly on very sensitive data.
Great. So that concludes the panel. A round of applause for all the panelists.